Okay, kids, we're back. We're still trying to look at the whole idea of what light is. What is light? We did a little introduction to it yesterday, had you review some stuff that you learned in grade 11 and grade 10. And we're in this situation right now. I hope you watched the two videos from yesterday where Newton thought light was a particle. Huygens thought light was a wave, and evidence is starting to mount to the point where the wave model is really taking over the predominant scientific thought. And one of the things that really turned the tide, get it, wave model tide, was uh, the observation, finally, of light waves, light interfering with another source of light, so two sources of light interfering with each other, just like waves do. And this really started to turn the page on this. So since this was the one of the most important discoveries that started to get people to think, light's probably a wave, Huygens is probably correct, is interference, it's time that we review the whole idea of an interference pattern. You have studied interference patterns before. We studied it when we were looking at waves on a spring, and we found standing waves. We did this last year with nodes and antinodes, right? Then we were looking at interference of sound waves, and we played with tuning forks. We twisted them around and noticed sometimes it was loud, sometimes it was soft. I believe I had you kids walk in front of two speakers, and there were your two sources of sound waves, the two speakers. And some areas had constructive interference, it was loud. Some areas had destructive interference, it was not as loud. And we observed it, and it was very much a qualitative look at this. What we want to do now in grade 12 is put some equations to it. So make it very much mathematical. So what do we have here? We have S1, source 1, some vibrating source. Could be a light wave, could be a sound wave, could be a water wave source. It doesn't matter. These work, what I'm going to teach you work for all waves. And there's a distance d from it to the next source. And both of these are vibrating, and they're both creating waves. Could be speakers, could be sources of light. It could be your two fingers dipping into a pan of water. Just two fingers together, up and down, up and down. That could be the sources of waves. It doesn't matter. And there's a certain geometry to this that we want to talk about. What I've drawn right here is a midline. So that's halfway between S1 and S2. So it would be D and a half, D by 2 here, D by 2. And this midline is definitely 90 degrees to the line D, which shows the distance between source 1 wave, source 2 wave. And what happens is if you observe the waves that come from here and come from here, as they get out into here, there will be areas where they interfere constructively, and there will be areas where they interfere destructively. So we want to investigate that, and we're going to investigate that by looking at a simulation. So I'm going to put the link to this in. I've got example two sources, and I'm using sound waves here. You can pick other waves, right? But we'll use sound waves. You can play around with the other stuff. This works. And here is a sound wave creating uh, compressions and refractions, compressions or refractions. Or if it's a water wave, it would be crests and troughs, crests and troughs. There's one source, source 1. There's another source, source 2. And they're a distance d apart. Now, Here is the pattern I was talking about. Let me stop it for you. In this area right here, you have an area of constructive interference where crests from one meet crests from the other source, troughs from one meet troughs from the other source continually. This is an area of constructive interference. Here's another area of constructive interference. It's demonstrated by being either very, very bright and then very, very dark. Very, very bright and then very, very dark. And you will see the pattern is symmetrical. Here's the middle one, and then there's one on each side, and then again a little bit further, and so on. But I hope you are seeing there is this gray area between the areas of constructive interference. See these gray areas? Well, kids, you've guessed it. Those are areas of destructive interference, where a crest from one wave continually meets a trough from another wave in these areas, so you get destructive interference. And now I can restart this. It's kind of a neat, there's so many different things you can change here. You can go to a 3D view, right, which is kind of interesting. Here's an area of constructive interference. There's the area of destructive interference, one on one side, one on the other. All right, very low to zero real amplitude. And here we get a big supercrest, then a supertrough, a supercrest, and a supertrough. A lot of constructive interference there. There you have it. All right, it's just to help you visualize this. And as I said, we observed this with sound waves last year, but we never did any of the math. Just like last year, we had all that fun with magnets, but we never did any of the math. This year, we did the math. Well, similarly, now we're going to do the math behind it, so I hope you're ready. So we're back at our note. So what I've drawn here in yellow are nodal lines. They're actually not a parabola, but they're a hyperbola. If you're not familiar with this mathematical shape, it's y equals 1 over x. If you're not familiar with it, look it up. Look up the hyperbola. And it's not a parabola, it's a hyperbola, and in short distances they look very straight, line-like, but they're actually not. There's just a slight curvature to them. And what I've drawn here is an area of nodal line. There it is. So this is the first time you run into destructive interference, and then it's symmetrical on the other side. And then the second time you run into destructive interference, and it's on the other side. So since this is the first time, right, we call this line the first nodal line, or nodal line n equals 1. Nodal line n equals 1 is symmetrical. There's one on this side and there's one on that side. Now, the second nodal line, we call that nodal line n equals 2 because it's the second one. And what are we identifying here? Well, we are identifying a point which I'm going to call P1, which is any point on nodal line n equals 1. There it is. Any point. It represents any point. And what I'm showing you here is that there is a length between point P1 and source 1. And I'm going to call that length P1 to S1. And then there's a length here from P1 to S2. And I'm going to call that length P1 S2. And it's a length, so these are straight lines. Similarly, I'm going to pick a point P2 on, and P2 is any point on the second nodal line, or any point on nodal line n equals 2. And there you have it. Now, again, I'm going to identify some lengths. The length between point P2 and wave source S1 is known as length P2 S1. It's a straight line here. And the length between the point on this nodal line n equals 2, this length between P2 and S2 is right here, and it's known as length P2 S2. So I'm going to pause here. Take a moment to kind of get the lay of the land here. I've shown you a lot of information here. Take a moment to reflect on this. Okay, we're back. So I hope you realize that the distance here, P1, S1, and P1, S2, they're different. These lengths are different. So it literally takes a longer length for a crest to get to here, or I should say a wave, never mind, just a crest. The whole wave takes a longer distance for the whole wave to get to here from S2 than to get to here P1 from S1. So P1, S2 is longer than P1, S1. Well, if the path length difference, if the difference in length between P1S2 and P1S1 is half a wavelength, and it will ensure that a crest always meets a trough, since the lengths are a multiple of half a wavelength off. It's like shifting the wave by half a wavelength, and you will always ensure crest meeting trough. So that's what we have here. The magnitude of, probably put the line above, that would be better. The magnitude of the difference in length between P1S1 and P1S2 is known as the path length difference, and it is on the first nodal line, okay, n equals 1, that difference in the length is 1 times lambda over 2. Now, if we take a look at the path length difference on the second nodal line, if we take a look at the path length difference on the second nodal line, so it's a little bit further away, the difference in their lengths increases. But if you want it to be a path length difference that always produces destructive interference, it still has to be a multiple of a half a wavelength. And in this case, it's 3 times lambda by 2. It can't be 2 times lambda by 2 because 2 over 2 leads you to a full wavelength. And if you have a full wavelength path length difference, then you will ensure that the crest from one always meets the crest from the other. Trough from one source always meets trough from the other because you've shifted by a whole wave. So the difference always has to be on the half. So what can we learn from this? We can learn that in general, for any nodal line, so the nth nodal line, that's where we continually have destructive interference, nodal line, node, is shown by this equation here, P1S1. So it's not the first, it's not the any point on the first nodal line, it's any point on the nth nodal line, minus P1S2. That path length difference is always a multiple of lambda based on the half. So if you put a 1 in here, 1 minus a half gives you a half. First nodal line, lambda by 2. Second nodal line, put a 2 in here. 2 minus a half is 3 halves, 3 over 2. Put a 3 in here, right? And you get 6 halves, 5 halves, I beg your pardon. Okay? So it would be 1, 3, 5. Always has to be on the half to be destructive interference. All right, so I've changed the zoom here because I want you to take a look at the whole picture here. And what we want to do is we want to take mathematically a closer look at this thing Pn, any point on any nodal line. That's what we want to do. So we still have the situation here, S1, source 1, S2, source 2. They're still a distance apart from each other, all right? And point Pn is very far away. Okay, let's say source 1 is on the one side of your desk, source S2 is on the other side of your desk, and like this is so far away, it's like on the other side of the football field, very far away. So we remember from what we just learned that there is a difference in the length that the wave had to travel. So PNS1, this distance right here, the one on the left, all right, minus PNS2, this shorter distance right here on the right. That is known as the path length difference, which most teachers, most physicists, most mathematicians will call delta L because there's a difference in the length between the two of them. And I'm going to show you where delta L is. It's right here. Okay, that distance right there is how much further the wave has to travel to get to point Pn if it starts from source S1 compared to source S2. And I'm going to label that point right there, which is showing how much length we have to delta L, what the path length difference. I'm going to label that point right there as A, and I'm going to draw a line that's 90 degrees to it right there. So let's read some of the stuff I wrote here. At these large distances, the hyperbola nodal lines approach being straight lines. So these two approach being straight lines. Now something else that you really need to wrap your head around. As Pn, any point on any nodal line, as it starts to get towards infinity, meaning as Pn gets further and further away, so I mean it's not on the other end of the football field, while your two sources are on either end of a desk in our room. Let's say Pn is, I don't know, where Jupiter is. This is far, okay? So as Pn approaches infinity in distance from the two sources, S1 and S2, then the lines PNS1 and the PNS2, these lines right here, okay, they start to approach being parallel to each other. They start to approach being parallel to each other. And the line AS2 really starts to be perpendicular for both the line here, AS1, and the line here. This line here starts to be 90 degrees to both of them. All right, starts to be 90 degrees to both of them. Let me show you what I mean by that. Here is S1 and here is S2. And let's say we have a point right here, any point. Well, you see, here is the distance between the two of them. Now, as I extend Pn to be further and further away, right? And let's pretend these are straight lines. As I make Pn further and further away, look what's happening to the lines that I'm drawing. Look what's happening to these lines, right? These lines are starting to move this way. Look at them. See, it opened up. It opened up. So if you were to think of a line here and measure the angle, look, the angle for the line keeps getting bigger and bigger and bigger. And same thing on this side. So if Pn approaches infinity, so it's not even on this page, and I redraw this, so Pn is, I don't know where Jupiter is, well then, for all intents and purposes, that's not a very good straight line, but you get the idea. For all intents and purposes, this line right here is 90 degrees, and that line right there is 90 degrees. So that's what I was talking about in the example. That this point here is so far away, you can basically consider it, and it doesn't look like it in the diagram, I get it, but they are basically 90 parallel to each other. That's a very important point. Now, let's take a look at this triangle right here. And I'm going to define an angle right in here called theta n. It's theta n because it's the angle here between the line D and this side here, AS2, all right, and it's defined by the any point on the nth nodal line. That's why it's theta n. And if I take a look at this, opposite over hypotenuse, because I got a 90 degree in here, so my D becomes a hypotenuse. Opposite over hypotenuse becomes delta L over D, and it would equal sine of theta n. So now I'm going to rearrange this. And I'm going to get delta L is equal to D sine theta n. But I know from my previous work, for a nodal line, delta L, which is the path length difference, remember we just did that a few moments ago? It has to be n minus a half lambda. It has to be n minus a half lambda. So now I'm going to rewrite this equation in its most famous form. N minus a half lambda is equal to d sine theta n, when n is the first nodal line, the second nodal line, the third nodal line, the nth nodal line. So it's giving us a relationship between which nodal line are we interested in, what's the wavelength of the wave that's creating the interference pattern, how far apart are the two sources, right? And at what angle to this line here will we find this point Pn? It's giving us an angular location. Now, here, there are physical limits to what we're doing. So what's the largest n value that actually makes sense? It's basically saying, well, how many nodal lines are there on one side? On one side, we want to maximize n. Well, to maximize n, we go back to this equation, and we want n to be as big as it possibly can. Well, d is the distance between the sources. Lambda is the wavelength of the two sources that are producing the interference pattern. The only thing we can change is theta. The only thing we can maximize, make as big as possible, is sine theta. Well, the biggest that sine theta ever gets is 1. Sine fluctuates between 0, -1, 0, +1. I think you all know the sine function. So I'm going to make that 1. So now I have n minus half lambda is equal to d. And I rearrange this, and I have now a way of finding what is the largest possible n value for a particular interference pattern made by a wave of a certain wavelength and a known separation between the two sources of the wave. All right, now let's take a look at this situation by taking a look at it not so much in an angular view, but in a linear view. So instead of being really worried about what is this angle right here, theta n, I want to know how far away is this point Pn from the midline, which is a right bisector. So think of a right bisector between S1 and S2. What is the distance xn from that right bisector to the point Pn? So I'm trying to describe the location of Pn not in an angular sense with theta n, but in a linear sense with xn, a distance from the right bisector. So what have I drawn here? Well, I still have source 1, still have source 2. I've labeled this dot right here C, which is the center between them. They are a distance d apart. That is still true. I've drawn this line here, which shows the path length difference between a wave leaving S1 and a wave leaving S2. I've drawn that. And I'm telling you now that Pn is approaching infinity. It's very far away. So far away that the line Pn to S1 is parallel to the line Pn to S2 and is parallel to the line Pn to the center. That they are very, very far apart, so far away here, this point, that these three lines are basically parallel. Basically parallel. Think about drawing a line from your left shoulder to Jupiter, from your right shoulder to Jupiter, from your middle of your chest to Jupiter. I mean, Jupiter's so far away, those three lines would be parallel. And for all intents and purposes, those three lines would basically be of equal length. I know it doesn't look like it here, but this is approached infinity. So the length Pn to S1 is equal to the length Pn to S2 is equal to the length Pn to C. So let's call that length L. L. Okay, let's call that length L. I'll give you a moment to think about this. So let's continue here. We still have our angle theta right in here. It's still theta n. Right here would be the complementary angle to theta, which I'm going to call phi n. So if that's theta n, that's phi n, and we've got 90 degrees in here, that means that this angle right here is also theta n. That's the angle from the right bisector to the middle line. That would also be theta n. So that means I can take a look at that and say, look, I have opposite to theta n is xn. The hypotenuse is L. Here's my triangle, goes from here to here to here, right? There's one part of the triangle, there's another part of the triangle, there's another part of the triangle. So the hypotenuse is L. So xn over L, opposite over hypotenuse, is sine theta n. So I can now rewrite the equation that I just had and replace sine theta n with xn over L. And I get n minus a half lambda over d is equal to xn over L. Or I can rewrite it and say n minus a half lambda L over d is equal to xn. So what have I done here? Now I can tell anyone how far away from the right bisector is any point on any nodal line. All I need to know is which nodal line are you interested in? Plug in the number. What's the wavelength of the two waves that are interfering with each other? Plug that in. How far away is Pn from the middle point between the two sources? And how far apart are the two sources from each other? And I have an equation to tell you how far this nodal point is. So now I have a way of describing the nodal point in a linear fashion. So now listen, a lot today, this is a very mathematical um, lesson. So maybe you want to go over it again. Be sure you read the textbook for sure, for sure, for sure. Take your time with it. I'm not assigning any homework questions today. I just want this to sink in. All right. This is a little bit of a view of some of the lectures that you're going to be getting next year, where there's very highly mathematical, a lot of mathematical reasoning, a lot of limits, as this approaches infinity, as this approaches zero. These are really important uh, thought processes that you, as a growing student in math or science or engineering or technology, you're going to have to start thinking in these ways. So don't be afraid of this lesson. Don't be afraid if you don't 100% understand it all. It's going to take time. This is the first time you've seen this. All right. I know when I studied this the first time I saw it, I didn't get it. I remember looking at my teacher, my professor, like, what are they talking about? But I went home. I read the textbook. I went over the note again. I started thinking about it. I went line by line by line to figure it out. And then it started to sink in. It's sort of like, the effort that some of you put in to defeating, Assassin's Creed or something. You put in all this effort and then, slap chat your buddies and say, look, I conquered this video game. You put a lot of effort into it. You got to put a lot of effort into this type of understanding of mathematical reasoning and mathematical proofs and progression. That's the only way you're going to be successful at the understanding of it, through blood, sweat, and tears. Have a great day. Bye bye.